Okay. Okay, well, welcome again to the second talk, and this is going to be by Fernando, who's going to tell us about arithmetic on non-standard binary sequences.
Yeah. Well, thank you, everyone. I'm glad to be here. Thanks, Ed, for organizing and hosting. Yeah, so Zach was talking about consistent computability theory, and at some point he was asking, well, how exactly a machine that does this kind of weird thing would look like? And this is a question we have been tackling in several ways, and I've been approaching recently this question in terms of actual computer circuits, right? So I'm going to be talking about
Well, here.
Exactly. No, I think I have to click. All right. Yeah.
Okay.
So I'm going to be talking about something I proposed in a previous paper called Done circuits. This is simply a way to implement non-classical logic gates and circuits using the principles of Done semantics. And now the whole reason I wrote that paper was really to get into the topic that I want to discuss today, which is there really a way to think about binary sequences in a non-standard way, such that we can use familiar methods or familiar machinery even to say that we are computing some sort of inconsistent number or having some sort of inconsistent computational process. So I will talk a little bit about the basics, the background ideas, which are Done semantics and this Done circuits proposal that I just mentioned. Then I will show you my most recent ideas about how to define different kinds of binary sequences. So we're going to extend the idea of what a binary sequence really is, given the framework of Done circuits. And finally, I will show you a little bit of the ideas or directions that I have so far about what it would be to be actually computing arithmetical operations like addition, given this kind of sequences and these kinds of circuits. All right. So for those of you who don't really know about this, this is called the von Neumann architecture. My titles can't be. I think
Actually, can you read okay there?
Yeah.
Because I don't know.
Yeah, I think that'll go away. Yeah.
Great. Cool. So this is the von Neumann architecture. It's pretty much a general design of how a computer should work, or which kind of parts should have for it to work. And I'm going to be focusing on this little guy here called the arithmetic logic unit. In a regular machine, that's your typical classical truth tables given, in the form of classical logic gates. And those guys are really all you need to perform arithmetical operations. So it makes sense that if we're going to turn away from classical computation, then we just have to think of those operations in a non-classical way, right? So these are your standard logic gates. You have seen those before. Of course, these work in a fairly standard way. You have electric current flows, and these gates are meant to control the flow of this current in a way that we can actually represent information logically. And of course, this all works with binary sequences of numbers representing all sorts of informations, not only numerical information, but yes. So this is the standard story of all our machines are working with those kinds of logic gates, and the information stored and handled in those machines is represented in this particular fashion, right? So in particular, when it comes to arithmetic, what we do is use the classical logic connectives to build particular circuits called adders, or for other sorts of operations, multipliers, subtractors, and so on and so forth. But all of these representations of arithmetical operations are really just concatenations of formulas and yes, connectives between them, right? So this is a half adder. You want to take one bit and add it to another bit, then you simply do that, and you get exclusive OR is going to be the addition of those bits, and then if there is a carry for that addition operation, then you compute that as a conjunction of those. Then, if you want more addition with more than one bit, which of course we want that, then you need to think of something called full adder. Again, we want to have some sort of sum given by the exclusive disjunction of the bits. C in is the carry that came as an input from the previous operation, right? And then this is going to generate another carry when you compute these bits together. So if you remember how to add binary digits, this is exactly doing that. You have to carry the 1 and move it to the next place of the addition, right? So this is exactly that. And the more schematic way of representing all this information is through something called ripple carry adder, right? So you start with a half adder, the little circuit I showed you first, and then you chain those through full adders, right? So for a Kantian sort of example, if you really want to show that 7 plus 5 equals 12, using this kind of construction, what you really have to do is take binary sequences like 0, 1, 1, 1, this is a representation of 7, 0, 1, 0, 1 is a representation of 5, right? And think of each bit of the sequence as a different formula, let's say, right? As a different logical object, right? From the right to the left, you name those bits. A0 is 1, A sub 1 is 1, A sub 2 is 1, A sub 3 is 7, right? So we do that. Similarly for B, and then you feed those guys into the circuits that I just showed you. You perform really a truth table of that. There's nothing of not other sort of computation than it's different from the one that is defined by the connectives, right? And this is going to give you a series of sums, series of carries, and in the end you end up with sequences like 1, 1, 0, 0, which is 12, right? So this is just a standard way of how addition is performed, and I want you to remember that in particular, because I'm going to be using that next. All right. Well, so that's like a refresher or an intro, or if you have never seen that before, that's the background information for the talk and the circuits idea. Okay, so as you know, I'm working on our consistent computability theory with Zach and Jack, and we have been rethinking a lot of the concepts involved here, and I find this passage, this fragment in Richard Sylvan's work, which is I think very compelling to me, and I took it very literally as an invitation to do this. Is thinking about relevant computer science and relevant AI. And at what point he says, well, dominant logic is classical two-valued. Computing hardware is precisely shaped in its two-valued image, and I think that's exactly right. I showed you just exactly how that works. But there is nothing essential or God-given about this. Machines could be constructed just as readily open enough to match any finitary system of valuations, not just, all right, that's cool. And he thinks that for this computer science and AI program to be carried out, you can go two ways. There's a hard way, there's a soft way. The hard way is the one I'm going to be focusing on today, which is the one that modifies the hardware. I'm not particularly restricting the results to relevant logic like Sylvan would like to have, but what he calls the soft way is something that is to some extent already done, right? Like change the ideas change the logic that's operating in the software to some extent. So I think quite literally about this idea about rewiring the computer for it to be for it to be different. And this ideas also go back to the works of Belknap about how a computer should think, right? He was already thinking that computers can be supplemented with databases in which you may have some way to say that the computer has been told that something is true and has been told that it's also false, right? So these ideas are already floating up in Belknap's works, and it's very much related to the origins of FDE and so on and so forth, right? So I said that my idea about circuits is following the principles of Don semantics, and they do so quite literally. So in a sense, my circuits are just another way to put Don semantics, right? They are completely equivalent. It's just perhaps different notation, conceptually speaking, if you think of that. But anyway, so you guys probably know already Don semantics. The way I'm presenting it here is just take a evaluation function, assign subsets of the set 0, 1, right, to propositions. That's going to give you things that we would like to interpret as truth only, both true and false, neither true nor false, and false only, right? We assign those sorts of values to propositions, and then what we do next is to extend that interpretation, valuation to an interpretation which is a non-functional relation, right? So this is a very typical, or what it's called today, the relational semantics is just another name for this, right? So this gives you a framework in which you can work without equalities, but with membership relations, right? So this is probably something you have already seen before. Okay, so right, so when you work with Don semantics, you separate truth and falsity. You have truth clauses, you have falsity clauses. Truth is not the negation of falsity. Falsity is not the negation of truth. These are separate things we have to consider, right? So for any given connective, we give truth and falsity conditions. Okay, so for instance, conjunction is true if and only if each conjunct is true. And we have to say that's not enough for it to be, that does not give you the cases where it's false. So you have to say the conjunction is false if either conjunct is false, and so on and so forth. Okay, so truth and falsity are handled separately in Don semantics. And that's a key thing for what I want to show you about the circuits in a minute. This is your standard truth tables, okay? When you look at truth tables in classical logic, you can think of those arrangements of zeros and ones as binary sequences as well. So you know that I'm going to be looking at this sort of binary things as binary sequences too, right? That's coming up in a minute. Okay, so I have said this before. To be true is not the same to be not false. To be false is not the same to be not true. Okay, right. So small facts about Don semantics. You can use this to represent. You can give a Don semantics presentation of m-valued logics that have values between 1 and 4. I guess you can say that you can also do it for more values, but I'm just stating this as a restricted sort of result for now. I don't need any more power. But if you have a 3-valued logic, you can use Don semantics to give a presentation of the truth tables of the connectives there. You can also do it for you can also do Don semantics for different consequence relations, like those like ST, which are mixed consequence relations. and so on and so forth. So you have this little MIT theorem. And note that this is not, this is talking mostly about truth tables, but we also know that we can use Dunn semantics for intentional logics as well, which is not a topic for today.
Fernando,
Yeah.
don't you need to specify that these values are, especially when it's 4 values, it's going to be like not linearly ordered, but more like a diamonds, right? So it can't be any arbitrary 4-value logic there in the theorem. Am I right?
Yeah, well, in the proof, I do talk about the order and the values you have to pick. So if you want, because you have to think about designatedness originally, then order matters there. So I give a sort of map about how to interpret the order of those values into this interpretations that we have in Dunn semantics.
But you're thinking of giving it Dunn semantics even for the linearly ordered case?
Yeah, because we could say
Yeah.
H system.
Yeah, I think so. And then,
Okay.
yeah, I think that's not ruled out. Well, at least I'm going to say that immediately. Even if it's not, I guess I'm not. It won't affect the results about computation that I want to reach. This was just like some sort of framework that I was developing and trying to be as general as possible. Yeah, so little facts, I guess. Okay, so here's the idea, right? So in classical circuits, what we have is a single electric current that represents truth and falsity at the same time, right? So if the current has high voltage, then that's interpreted as truth. If the current has low voltage, that's interpreted as false. And then your gates perform computations in that. Now, I told you that Dunn semantics handles truth and falsity independently, so we should have, this is my proposal, 2 different electric currents, one for truth, one for falsity, so we should have 4 different possible states. So the truth wire, let's call it that, can be on or off. On is high voltage, off is low voltage. And similarly, the falsity wire can be on or off. Okay, so this is mimicking Dunn semantics, and this is why I'm calling this Dunn circuits. So here's a little picture of what I have in mind. Again, we have the diagram for your standard representation of logic gates, but in this time we have 2 wires for each thing, right? So the dotted lines are for the falsity wire. The other standard line is just the truth wire. It doesn't really matter which is which, but you have this double wire setup because you want to handle truth and falsity independently, okay, as it is done in Dunn semantics. So yeah, so what happens is that then you can think about the logic gates quite differently as, well, I formulated this in sort of a ordered pair structure, but I guess it doesn't really need to be ordered. Well, anyway, I chose this structure. So if you take negation, for instance, then if the truth wire is on, then negation turns it off. And if the falsity wire is off, then negation turns the falsity wire on, right? So that's your first case. And then you do the same for the other cases. This is just mimicking the De Morgan negation that I showed you before. And of course, you can do the same for conjunction, disjunction, and any other sort of operation that you had in Dunn semantics, right? So in the paper, I just show how these 2 things map together and how the truth conditions are met, right? So this is a little diagram of a dialethia, right? So if you ever wondered how the true contradiction look like. Well, maybe this is a way of picturing it, right? So this is a circuit of A and not A, but in particular it has a configuration in which both cables have electric currents with high voltage, right? So if one wire is a truth wire and the other wire is a falsity wire, here is a diagram for a true contradiction, right? Okay, I think it's kind of neat. And we go back to the idea that really matters to me today, which is arithmetic, right? So if I go back to the others, I can really use the same circuits that classical computers use. Okay, we still have disjunction, conjunction, negation, exclusive disjunction, and so on and so forth in Down semantics, and the truth conditions are the same, really, as they are in classical logic. So there should be nothing in principle that stops us from using the same sort of circuit structure for arithmetical operations. That was the thought. Okay, so in a sense, we could think of binary sequences in this Down semantics presentation in this way. Like, I'm using curly brackets because that's my notation in Down semantics. But if you think about it, it's pretty much the same as not having curly braces. Or maybe that's a trick, I don't know. But 111, which would be the standard way to represent 7, as a binary string in Down semantics, maybe could be represented as 111, but all of those inside curly brackets. And then the interesting thing is, you may have strings which are non-standard, right? Strings which have glotty bits and strings which have gappy bits. And the question that I left open in the paper was, well, what exactly happens with those sorts of strings, and can they really be thought of as representations of binary numbers to some extent, or not? So that question is the one that I'm trying to approach in the talk today, right? So it turns out that if you fit standard classical bits or standard classical representations of numbers to this Down circuit for the adder, you will get the arithmetic that classical computers gave you. Okay, so it's no problem there. Just some little facts about Down circuits. You can use them to decide logics which fit these descriptions being for value. Maybe I should discuss more about that with Hitoshi. But anyway, I design some strategy to decide logics because the only reason classical circuits decide classical logic is because of the deduction theorem. You can check if an argument is classically valid if you check the conditional version of the as a tautology, and you can do that with a circuit. But if you were in LP or K3, for instance, that wouldn't work. So I designed a different way to do that. And that way is actually very much related to Hitoshi's work on Bell-Down logic with the Bass delta. This is the Bass delta with a different notation. It's just telling you when something is true. So I sort of designed kind of deduction theorem that holds not inside the same logic, but between a logic and an extension of it, where the extension is given by adding this truth connective or whatever, right? So that was a trick to prove decidability. That was also the trick to the following idea. Okay, so let's say that a decision circuit is just a Down circuit that computes that formula that I just showed you previously, right? And you get, and you get things like an argument is logically valid if the decision circuit outputs truth only for any configuration, for any input configuration, And you can relate this to soundness and completeness results as well. So if you have a natural deduction formulation for these logics, you can show that if that formula is provable in the extension, then the decision circuit has to output the truth only for every input configuration, and then soundness and completeness with respect to the circuits also follow. And yeah, so those were pretty much easy results, I think. Yeah, and in particular, I can decide classical logic. I can have soundness and completeness for classical logic as well with my circuits, and in particular, I can recover all binary arithmetical operations that are that come from classical circuits, right? I just use standard bits or standard sequences for that and feed them into my adder. Nothing changes there. Right. That's where the paper stopped. And then as a continuation, I thought, okay, well, we have to kind of set some ground rules or some terminology or method or something. Think about binary sequences. So I'm considering the power set of 2, right? These 4 different interpretations of Dunn semantics. I'm considering those as an alphabet of a formal language that I want to be closed under Kleene star, right? So I want to have all the possible strings that result from concatenation of the subsets of 2, right? So this is a fairly standard construction that we use in computability theory. We just take strings of symbols of a language and concatenate them and call those valid strings of a given language. So my language is going to be concatenations of 1, 1, 0, and nothing and 0, right? I do have an empty sequence because that's by construction, but that empty sequence is not to be identified with this sort of member of the language, right? It's the empty set, but that doesn't mean that that is the empty string. They have different lengths, and moreover, the empty string is the identity of concatenation in the free monoid of concatenation given by Kleene stars, right? So little things about that very standard procedure, and then terminology. Okay, so consider a string in this given language, right? It is of length k. I'm enumerating from 0 because 0 is the natural, I think. All right, I'm enumerating from 0 to k minus 1 the bits that compose the sequence W. Okay, now each of those is a bit. If the bit is of the form just true, then I'm calling it a T bit. If it's of the form 1, 0, it's a B bit. If it's empty, that's an N bit, and if it's false, it's just an F bit. Okay. Then, of course, this is what I use to define Glotti sequences. So a sequence is Glotti if it has a B bit. A sequence is gappy if it has an N bit. A sequence is a Dunn sequence if it has both gaps and B bits and N bits, right? And it's a standard if it doesn't have any Glotti or gappy bits or whatever, and otherwise it's non-standard. Okay, so this is my terminology. And of course, you can say, well, the computer science really doesn't take the power set of 2 as binary sequences. They take 2 and close it under the Kleene star, and you have this 1, 0, 1, 1, 1, 0, 1, 1, blah, blah, blah. And now I want you to compare that to this subset of standard binary sequences, what I just called standard binary sequences. Of course, there is a bijection between those. A very, very trivial bijection between those would be send the empty string to the empty string, and then for the other strings, just map them to the unitary of the bit. This is fairly standard bijection one can build. So in a sense, when we think of binary strings of 2 close under the Kleene star as binary representations of numbers, then by this bijection, we can also think of these standard numbers as representations, standard sequences as representations of binary numbers, even if they have this curly braces around. It doesn't matter. They can be thought of as representations of binary numbers, even if they are notationally more cumbersome, right? So that's, I think, an acceptable first step that we can take for the next thing, which is, okay, well, what about glotty or gappy sequences? Can those be also considered as representations of binary numbers in some sense? So for today, I'm only going to be focusing on glotty sequences. I have some, I don't think the idea that I present today here will work for gaps yet, but maybe you have some suggestions. Okay, so for glotty sequences, take the set of all glotty but not gappy sequences. Okay. Now, if you have a standard binary string, okay, of length k greater than 0, and we fix some set of indices, okay, which are the 0th bit, the first bit, the second bit, and so on of a k of a string of length k. Okay, that's the index here. And for any sort of binary, standard binary string v, there will be an associated overflow function, right? So what this does is, this little b is a natural number considered as a binary string, right? So it could be 5 or 7. Then we take some index, which tells us which of the bits in that sequence is to be overflown, right? So if you had originally just 1, then now you have 1 and 0. If you originally had 0, then now you have 0 and 1, for instance. And you can do that for individual bits, or for multiple bits, or for all bits. That's an overflow function. The idea is that if you have information stored as a binary string, and it somehow gets corrupted, like there's some physical process that damages the storage or whatever, then you may have some bits that are now inconsistent bits, right? And in general, using this overflow function, the property that I want to have is that the glotty sequence that we obtain from this function is an inconsistent representation of the standard string. It's an inconsistent representation of the number. Because the number, the standard string, is contained in this non-standard string, okay? You can sort of look at the non-standard string and say, okay, I can see that amongst all the noise, my original string is also there, right? That's the idea. Okay, so that's about the overflow function that I just explained. Take the set of all representations of a binary string, or take the set of all inconsistent representations of a number, right? Of course, there are going to be 2 to the length of the string minus 1 representations, because this is just a construction on the power set, and we don't want the empty set around. Now, of course, if you have 2 different standard binary strings of the same length, they will have common representations, right? So if you want, like if you take numbers with 3 bits, by using the overflow function, you will generate inconsistent representations of those, which are common to each other. Okay, so for instance, if I take 1, 1, 0, 1, that is an inconsistent representation of 5. You can see that 5 is in there. 1, 0, 1 is 5, standardly. But this is also an inconsistent representation of 7. because you have 1, 1, 1 in here. Okay, so this is a common representation for 5 and 7. And of course, there are other representations that will only appear in one but not the other. Like 1, 0, 1, 0 is going to be a representation of 5, but it's not a representation of 7 at all, because that would need a 1 here in the middle. And a similar thing can happen for 7 and 5, right? So these are inconsistent representations of numbers. I think you get the idea that I have. Like, just look at the sequence and see if you can find the standard sequence contained in it, even though you have some noise around the bits. And then, of course, the idea is to use these representations and add them together with the others that I showed you before. Okay, and if I do that, I actually get correct results relative to standard arithmetic. So if I take a standard representation of 5, an inconsistent representation of 5, and add it to an inconsistent representation of 7, I get an inconsistent representation of 12. Okay, so I've been toying around with this, and it always works. And it should work because it's the same sort of logical construction of addition, right? And you can take inconsistent representations like that for 5 and add them to standard representations, okay, without modifications, right? Like this 7 right here. And you will also get the representation of a number that you should classically get. Okay, so this works apparently. 5 plus 7, no matter how you represent it, will give you 12. But now there's a weird case, which I like very much. There is a common string that represents any numbers. So if you have all numbers of some length, all of them will be represented by the string that has b bits in all places, right? You can find all binary sequences contained in strings which are only composed of b bits. So take any strings of length 3, right? X and Y are the numbers being represented by those. If you add those together, you get a 4-bit string which is representing another number. So when you add these maximally inconsistent representations of numbers together, you will get the correct equations back, like 4 plus 5 equals 9, 7 plus 7 equals 14, whatever. But you can also capture, or you will also capture in this sort of situation, wrong or additional equations. You will capture 4 plus 4 equals 9, for instance, right? Because you can read that the sequence 9 is contained in the sequence obtained through the adder, right? And my claim is, this is what inconsistent computation would look like if you think of it like a machine. Like it's performing what it should do, like it's computing 4 plus 4 equals 8. It does what it should, but then it's also doing something else, like 4 plus 4 equals 9. But the thing I like about this circuits approach is that it's doing so in a controlled way. It's not an arbitrary way. It's not going to give you any equation for a given case. It's giving you some set of equations that hold for numbers with appropriate lengths as sequences, right? So I think that this is one way to think about what inconsistent computation can be. And a day or two ago, I thought, okay, so there should be a neat theorem for this. So if you take 2 standard binary strings and have inconsistent representations of those, then the addition of those inconsistent representations should correspond to the standard addition of those numbers being represented, right? That's a theorem that I want to get. Of course, I haven't proved this. I think I should prove it by induction, and that's pretty much the state of the research so far. That's what I have so far. What I want to do is to check if this story also works with multipliers, subtractors, and other sorts of circuits. of course, obtain theorems like for multiplication and other operations like that I just showed you about addition. And if everything works, well, then I think I should have all recursive functions in this sort of setup. But my real question is, can I have more than these? Can I have other stuff around, given that I have this additional structure floating around? And as I mentioned to you, I think that the idea that I pitched today will not work when gaps are allowed in sequences. I don't really know what to do with gaps, because remember, the overflow function is not erasing any information that you had stored in bits before. Whereas a dual function to the overflow function will erase information and generate gaps instead of gluts. And I don't think that you can so naturally interpret binary strings with gaps as representations of numbers. But anyway, that's a different problem for a different time. I don't know if I should abandon gaps and stop thinking about them. I don't need to think about them now. I just need to keep looking at gluts and see if all these directions I want to get to are actually feasible. Yeah, so that's it. Yeah. Any questions?